Paul Werth also spoke yesterday, so this is part of a two-part webinar series, and he's going to be speaking about critical fire weather patterns today in the western United States. And yesterday he described critical fire weather patterns in the eastern U.S., Canada, and Australia. So if you'd like to find a recording of that first part of this set of webinars, that's on that Fences and Fire Practice webpage now as well. But Paul retired from the federal government service in 2005 after 36 years as a fire weather meteorologist with the National Weather Service and the U.S. Fish and Wildlife Service. Before that, he served as a weather forecast for the United States Air Force in the space program at Cape Kennedy, Florida, and worked on the Apollo 14 through 17 programs and numerous other space launches. He was the lead fire weather meteorologist at Medford, Oregon from 1975 to 1982, and he moved to Boise in 82 to serve as the NWS fire weather meteorologist at NIFC. In 2000, Paul accepted the fire weather program manager position at the Northwest Coordinating Center in Portland and was instrumental in developing the Predictive Services Unit. He's an experienced incident meteorologist working on 35-plus wildfires and has supported numerous wildland and prescribed fires from Oregon to Florida. He served on the South Canyon Fire Investigation Team analyzing the meteorological events that contributed to the tragic deaths of 14 firefighters on Colorado's Storm King Mountain in 1994. And with that, I will hand it off to Paul. There you go, Paul.
Okay. Should have it now.
Got it. Yeah, there you go.
Anyway, thank you very much, Josh. As Josh mentioned, this is a series of webinars based on a 2011 Joint Fire Sciences Program publication called Synthesis of Knowledge of Extreme Fire Behavior, Volume 1 for Fire Managers. And being a synthesis, this is a summary of knowledge of extreme fire behavior based on extensive literature search over the years. And some of the publications, for instance, that I use go back to the early 1900s. There is going to be a volume 2 printed here shortly. It's in final print layout now, and it's going to include a fuels chapter, which volume 1 doesn't have. And then many of the other chapters are going to have extended and expanded coverage. So look forward to that coming out in the next few months. Okay, this is a continuation of yesterday's Chapter 3 Critical Fire Weather Pattern webinar. And this one will cover the western United States, including Alaska. And the outline for this webinar is pretty much follows Chapter 3 in the publication. We're going to be talking about weather elements that promote extreme fire behavior, general discussion of critical fire weather patterns, regional critical fire weather patterns, including as many case studies as we can cram in here in this webinar. We're going to look at some predictive tools that fire managers and firefighters can use and monitor to see when the risk of extreme fire behavior and large fire growth is possible. And then we're going to finish up with a summary and talk a little bit about future research needs, knowledge gaps. Just might interject at this point that the authors in putting together this publication worked and developed an alternate definition for extreme fire behavior that is shorter but still covers all of the primary points that the NWCG definition holds. And the definition we used in this publication for extreme fire behavior is fire spread other than steady state spread, especially when it involves rapid increases. So anyway, going forward here, we're going to just define what we mean by critical fire weather patterns. And critical fire weather patterns are those atmospheric conditions that encourage extreme fire behavior, resulting in large and destructive wildfires. And what we're going to be looking at is the large-scale weather patterns, what we call synoptic weather patterns, the high and low pressure systems that can be 1,000 miles across. We aren't going to be dealing with local effects such as local slope and local canyon winds, which were already covered extensively in the first webinar of this series that dealt with extreme fire behavior effects caused by complex terrain. So what I have on the left-hand side, the graphic here shows the 500 millibar analysis across the northern North America. And what it shows here, this is a constant pressure map. So every point on this level is 500 millibars. But the isohyets, the lines that you see, are lines altitude in which that 500 millibar pressure is attained. So lower heights demark low pressure areas, upper level troughs, which there is one in this example in the Gulf of Alaska. A ridge of high pressure is over the Pacific Northwest into Western Canada, and another low pressure center near the Hudson Bay area of Canada extending down into the Great Lakes. And what you see when you look at the 500 millibar map, you see alternating low pressure areas and upper ridge areas. So you see a low, a high, and a low. And these are the weather patterns, weather features that we're going to be looking at this afternoon to identify which of these represent a weather pattern that could result in extreme fire behavior and large fire growth. So before we get into the patterns themselves, let's just quickly review what weather elements promote extreme fire behavior. And this is basically a review of S290, but I'm going to reinforce it here in that we're going to look at these factors and compare it to what is caused by these critical fire weather patterns. The four weather elements that we're going to be keying in on is low relative humidity or low atmospheric moisture, strong surface wind, unstable air, and then a little bit about drought conditions. And all the cases, the fire cases that I have seen in the past, and all deal with extremely low relative humidity for the area for the time of year. So I think this is a critical element that must be present in order to create a critical fire weather pattern. Strong surface wind and unstable air, the pattern also needs at least one of those. If it has both, that just adds more dynamics to create a large fire growth or extreme fire behavior. And then touch a little bit on drought. And drought primarily affects the fuels. So let's go ahead and just briefly review each one of these elements. Low relative humidity lowers the moisture content of fuels, especially the fine fuels that are easier to ignite and carry the fire, and really result in increasing the forward rate of spread. Low relative humidity also increases the spotting potential. And then we're going to talk a little bit about regional RH thresholds for extreme fire behavior. What I've seen in the literature, there's quite a large range depending upon the fuel model. It can range as a threshold as low as 10% to as high as 40%. And one of the interesting things that I found in my literature search was really early back into the 1920s and 1930s, there was quite a bit of research looking at regional RH thresholds. And Dagg in 1930 did quite an extensive research of large fires in Washington and Oregon and found out that 20% is a good threshold for east of the Cascade Mountains in Washington and Oregon. And frankly, that 20% still holds for much of the Intermountain area from Idaho, Montana into Washington and Oregon. And I used that 20% threshold on many of the fires I was on and found it to be very accurate. Strong surface wind supplies oxygen to the fire, increasing its intensity. Preheats the fuels as the flaming front is bent over by the winds on into unburned fuels. It increases rate of spread, increases downwind spotting, and produces wind-driven fires. And as far as spotting goes, Brian Potter's upcoming webinar on spotting will cover much more about the wind effects on spotting. Unstable air. Unstable air enhances upward vertical motion. It supplies more oxygen to the fire, enhances vertical growth of the smoke column, increases chance of gusty winds and vortices. Can result in plume-dominated fires. A lot of times is the result of Haynes index values 5 and 6. And unstable air can also create possibility of dry lightning. And again, as far as plume-dominated fires go and plume dynamics, that will be another one of Brian Potter's upcoming webinars. Drought. Drought lowers moisture content of both live and dead fuels. And in this picture on the right here, you see a lot of down and dead. And that's where drought would certainly lower the moisture content of those down fuels. And in drought conditions, that would add to the surface fire intensity and enhance the probability of getting crown fires. Drought also affects the foliar moisture in the crowns, lowering it. Drought affects the fuel availability, that is loading and combustibility. And drought is not always a prerequisite for large fires. In fact, many of the large rain fires I've studied in the Intermountain, Western Great Basin area, many of those fires actually occurred when the Palmer Drought Index indicated very moist conditions. I think a part of that is just because of the increased moisture increases the fuel loading of the grass fuels. So that's something to keep in mind. We're going to look at some publications here, early publications that investigated synoptic weather types associated with critical fire weather. And the first one was Schroeder and a host of other co-authors in 1964 compiled a document, synoptic weather types associated with critical fire weather. And what Schroeder and the others did was divided the lower 48 states into 14 different climate zones. And each one of those climate zones, they looked at both surface and upper air patterns that resulted in either high to extreme fire danger or in large fire occurrence. And their conclusion, basically for the western United States, is that most critical fire weather patterns are associated with upper level troughs, jet streams, and cold fronts. And along the Pacific coast, patterns producing firn winds are the most important. That's Washington, Oregon, into Southern California. Another very important document was authored by Nick Nimchuk from Canada in 1983. And the title of his publication was Wildfire Behavior Associated with the Upper Ridge Breakdown. And as far as I can tell, looking through the existing literature, he was the first one to coin upper ridge breakdown. And what Nimchuk studied was wildfires during the severe 1981 Alberta, Canada fire season. And he looked at the relation of the period of large growth of those fires to 500 millibar and surface pressure patterns. He identified a lifetime cycle of upper level ridges in 3 distinct fire weather stages. And he clearly identified the breakdown rather than the presence of the upper ridge as the trigger for extreme fire behavior. Now we're going to look at his 3 stages and see how the stages of an upper level ridge affect some of the critical weather elements that we earlier stated here. And the first one is the establishment period. And the graphic on the right here, just explaining this a little bit, it shows a 4 corners high. That's a semi-permanent high pressure over the western states during the summer fire season from July through early September. And the establishment stage would be at the leading edge or the eastern edge of this high pressure area. It is an area of rising 500 millibar height, so you have warming aloft, and that produces stable conditions. It is also an area where at the surface a high pressure would be centered right about in this area right near the tab here for establishment stage. You would have light winds, low relative humidity, and the fuel moistures would be starting a gradually drying trend in this establishment period. And because the very stable conditions, there is low lightning risk involved in this stage. Now the second stage is he called initial weakening, and that is characterized up in eastern Montana here, where you see a little dip in the isohyates here at the 500 millibar level, indicating a weak trough that is trying to move across the top of this high pressure area. And he called this an initial weakening period. And because there is cooling aloft involved in here, you have more unstable air, increased chance of lightning, very well could be dry lightning. There would be more wind involved and would be continued low relative humidity. Now a lot of times in the summer out west here we see this initial weakening trough is passing over the top of the semi-permanent high pressure or the long-range high pressure area centered over the 4 corners. Once that trough moves across the top of the ridge will build back in behind it. And so you get a succession of these weakening troughs that pass either up the west side or the north side of this high pressure area. And his final category or final cycle was a final breakdown, which shows a stronger trough moving into the Pacific, off the Pacific Ocean. And in this case, the final breakdown would involve a significant diminishing to the strength of this high pressure area, and it more than likely will not rebuild again after the final breakdown. But the final breakdown is characterized by a cold front passage with unstable air, lightning, strong shifting winds, low relative humidity initially, but after the surface front moves through, there would be increasing humidity after that. So those were his 3 stages. And taking a little further depth, looking at this from a 3-dimensional view, the graphic on the left is from a paper I and Rick Ochoa published in 1993 looking at Idaho wildfire growth and the Haynes Index. And this is a graphic we use to show a 3-dimensional view of breakdown of the 500 millibar ridge. The solid lines here are demark the area where the high pressure is. It's centered over the Four Corners area. And again, these are ISO heights around the center of the high. And as you get to a low pressure trough trying to push into the Pacific Northwest, you have decreasing heights at the 500 millibar level. But at the same time, the surface thermal trough that is typically centered over the lower Colorado Basin and up through California, Central California in the summertime, is situated underneath the breakdown of the upper level ridge, the falling heights. And this is the area where the air is warmest at the surface. So you have cooling aloft, warm air at the surface, and that results in an unstable air mass with a good chance of thunderstorms and possibly dry lightning. The fact that these contour lines in the 500 millibar height are closer together, you have stronger winds aloft, possibly a jet stream embedded in the area where the heights are falling, and strong winds aloft can work their way down to the surface through downward momentum. The surface thermal trough has hot temperatures, probably the hottest temperatures at the surface, right in the center of the thermal trough, and the lowest relative humidity. And if by chance you happen to have dry air that is moving in aloft, a lot of times you can see this as dry slots in the water vapor imagery. A lot of times you have a tongue of dry air that moves in also as the ridge is breaking down. And if this occurs, you have moderate to high Ains index, and you end up with unstable air, low relative humidities, strong winds. And if you're in a drought situation, you have all the factors that really can produce extreme fire behavior and large fire growth. So let's go ahead and look at some regional fire case studies here. And first of all, we're going to look at the Southwest area, which includes Arizona, New Mexico, and West Texas. And the fire season there spans the months of May through October, but can extend the entire year in the grasslands of eastern New Mexico and western Texas. And there typically is a midsummer lull in the fire season during the monsoon season, which can last from July through September. So the critical fire weather patterns for this area: one, you have the breakdown of the upper ridge, and this occurs when upper level troughs moving inland from the Pacific Ocean are strong enough to push the ridge over the area south and east. Dry cold fronts can mix strong winds aloft to the surface with peak speeds of 40 to 50 miles an hour, not unheard of. Another associated critical fire weather pattern is the lee surface trough and dry line. And this occurs in eastern New Mexico and western Texas in advance of an upper level trough. A north-south dry line develops at the surface that sharply divides moist Gulf air from the Gulf of Mexico and dry air descending from the Rocky Mountains to the west. And I have an example of that that we'll look at here shortly. The final critical fire weather pattern is early stage monsoon. This is the onset of the south monsoon, can produce extreme fire behavior due to the combination of gusty wind, low relative humidity, and dry lightning. And this is usually the transition period from the hot, dry conditions in May and June to the summer monsoon in July. And what happens is the upper level high starts to develop or push northward over the Four Corners area, and over the southwest you have more of a southeasterly or easterly wind flow aloft, which advects moist air from the Gulf of Mexico in the region. The early stage of the monsoon, there's just enough moisture to get thunderstorms and dry lightning going, and it may take days to maybe a week or so, whereas the air mass becomes moist enough that there's quite a bit of precipitation with those thunderstorms. Anyway, one piece of literature I did find was from Crimmins, 2005, for the Southwest, and he examined extreme fire weather conditions in the Southwest from 1988 to 2003, so that's 15 years. And what he found was that over 80% of the days that had extreme fire danger or large fire growth occurred with broad southwesterly flow aloft and large geopotential height gradients. Again, that's the height values associated with at the 500 millibar constant pressure map. This is similar to the pattern identified by Schroeder in 1964 and is consistent with the breakdown of the upper ridge critical fire weather pattern. Okay, the first fire case study we're going to look at is the Cerro Grande fire in New Mexico. This burned May 7th of 2000. And the graphic on the left here is the 500 millibar height value for May 7th. And what it shows here is the upper level ridge that had been over New Mexico has been shifted eastward into the Great Plains and up into the Great Lakes area by this strong upper level trough that is pushing in from the Pacific coast. And you can see where a lot of these height contour lines are bunched together. There is a strong jet stream located right in where these contour lines are the tightest. Looking at the height values here, 552 and 556, that's really a strong upper level trough for early May. Normally you don't see height levels that low. But anyway, what happened on the Cerro Grande fire, it experienced extreme fire behavior. Strong southwest wind, gusts 75 miles per hour on the fire, which were located right in north central New Mexico. Experienced extremely low relative humidity. It was in a drought area. That day it burned 50,000 acres and unfortunately also 235 homes. So again, we had the strong winds, extremely low relative humidity, and drought. It appears that unstable air really wasn't that much of a factor in this particular case. But this is a satellite picture, visible satellite picture from that day, showing the fire over north central New Mexico and the smoke column that extends all the way over into the Texas and Oklahoma panhandles. The next case we're going to look is a dryline lee-side trough effect. This occurred in West Texas in February 27th of 2011. And again, the graphic on the right here is the 500 millibar chart. The area circled here is the area in which the large fires occurred, and it's also where the jet stream was located between the upper ridge, which had moved well to the east, and this closed low pressure center that is moving into Southern California. Again, these contours here, the height contours are really tightly packed, and it looks like the jet stream winds there. I see a value, observed value from El Paso there of 80 knots. So that gives you an idea how strong this jet stream was. But anyway, obviously extreme fire behavior that day. Multiple fires burned thousands of acres. Pretty much light fuels, grass fuels, burned numerous structures. Thousands of people were evacuated. Experienced strong gusty southwest winds, unusually low relative humidity at 5 to 15%. The Haynes index chart for that day showed the Haynes index of 6, centered right over West Texas. And again, this is a classic lee-trough dryline critical fire weather pattern that can see in February and March here coming up very soon. The next slide here shows the surface pattern at 1800 UTC for Texas and western United States. And this line here marks the dry line, which is really a very sharp line that demarks moist air from the Gulf of Mexico and dry air off the Rocky Mountains. The dew points on the east side of this line are running into the low to mid 60s. We're on the west side behind the trough. The dew points are in the teens. And then the cold front itself is some ways behind the dry line, and that shows a return to a little more humid conditions and possibly some showers. The satellite picture on the right hand is taken about the same time as the surface chart on the left side here. And again, this is your area of very low relative humidity in the teens. This happens to be the dry line, showing clouds and humid air to the east, very dry and clear air to the west, and then back beyond in the cold front is where the cooler temperatures, higher humidities, and showers show up. So this was a one-day event, but again, it was very dramatic and caused the evacuation of thousands of people there. The next area we're going to look at is Rocky Mountain and Intermountain regions, and that's going to pretty much include central and northern Rockies and the Great Basin. And fire season in this area ranges from May through October in the southern portion and June through October in the northern portion of this area. However, in the grasslands of eastern Montana, eastern Wyoming, eastern Colorado, and then to the Dakotas, Nebraska, and Kansas, fire season can start prior to green-up in February and March. Looking at the regional critical fire weather patterns, again, breakdown of the upper level ridge, surface thermal trough, very similar to what we'll be seeing throughout the west here, occurs when an upper level trough is strong enough to push the upper ridge east and south of these regions. A surface thermal trough, dry cold front producing strong wind, low relative humidity, unstable air, and possible dry lightning occurs during the breakdown of this upper level ridge. Another significant pattern for the Rocky Mountains, especially primarily the eastern slope of the Rocky Mountains, is firn wind Chinook wind pattern. And this occurs when strong jet stream winds blow perpendicular to the mountains, to the Rocky Mountains, producing strong surface winds and unusually warm and dry conditions for the season. This pattern is most prevalent in winter, but also can occur in spring and fall. And the early stage monsoon is similar to the previously discussed southwest pattern. The Four Corners upper high pressure system moves north and east, allowing moisture and unstable air from the Gulf of Alaska to produce dry lightning over the southern portions of this region. Fire case study, going to look at South Canyon Fire, Colorado, on example of July 6, 1994. Probably all remember this fire. 14 firefighters were overrun and perished as a result of a crown fire which overran their position. But this fire showed rapid transition to extreme fire behavior driven by strong southwest winds, gusts of 50 miles per hour. And then there was a cold front passage in here that shifted the winds around to the west and northwest. The relative humidity was unusually low, less than 10%. The air was very unstable, observed a Haynes index of 6 that day. And this is a classic breakdown of the upper level ridge pattern in a dry cold front passage. The two graphics below are taken from the fire report. This is on the left-hand side. This is the 500 millibar pattern during the day in relation to the fire. South Canyon fire was sort of in central Colorado. 500 millibar pattern showed a very pronounced upper level trough and even a little bit of a low center over in northwestern Wyoming, with the trough extending down along the Utah-Colorado border. At the same time, this is the on the right-hand side here, this is the surface position of the cold front at about 1800 Mountain Daylight Time that day. The front had already passed the area, looked like it had passed the South Canyon fire area about 3 or 4 o'clock in the afternoon, sometime in that time period. We can see also quite a bit of gradient, surface pressure gradient across western Colorado there. So again, this was a classic breakdown of an upper level ridge with the passage of a dry cold front at the surface. The next fire case study we're going to look at is the Yellowstone National Park fires, and we're going to look at September 6th and 7th of 1988. On the left-hand side here, this is the 500 millibar upper level chart showing the upper level pattern over western Canada and the northwestern part of the United States at 1200 UTC. That would have been early in the morning on September 7th there. Anyway, what that shows is the upper level ridge has broken down completely. In fact, it is flattened, and what's left of it has kind of shifted east into the Great Plains. A very pronounced trough from an upper level low in northern Canada extends down into Idaho. Very strong northwesterly wind jet of 70 to 80 knots is embedded right across eastern Washington, northern Idaho, and western Montana early that morning. During the day, extreme fire behavior developed both in Yellowstone and on fires in central Montana. Multiple fires burned 150,000 acres on September 7th in the park that day. Meanwhile, Canyon Creek Fire in Montana burned 160,000 acres and crossed the Continental Divide. This Canyon Creek Fire, once across the Continental Divide, was driven eastward by a strong Chinook wind that developed on the east slopes there. Experienced throughout this area strong gusty southwest northwest winds up to 50 miles per hour. Relative humidity was very low, 10 to 20%. Again, this is a classic breakdown on an upper level ridge, critical fire weather pattern that included Chinook winds in Montana. This is the surface pressure pattern for September 7th. The blue lines, two blue lines here indicate a double whammy on cold fronts. Both of them were dry. Early in the morning, one was just moving into northwestern Wyoming, and the second stronger one was pushing southward from Canada into western Montana and northern Idaho. And satellite picture taken from later that afternoon. You can see the distinct smoke columns. All the fires in Yellowstone National Park took off and ran that day with well-pronounced smoke columns extending just about as far east as the Black Hills. And this is the Canyon fire up in central Montana. You can see the smoke column there, very narrow and kind of twisting. This fire was probably sitting right under the jet stream at that time. Okay, moving on to the Pacific Northwest region. This is states of Washington and Oregon. Fire season typically extends June through October. While the fire season is shorter than other regions, these two states have experienced some of the largest and most destructive fires over the year. Regional climate fire weather patterns, again, breakdown of the upper level ridge, surface thermal trough. This occurs when an upper trough approaches moving onto the coast, pushing the upper ridge east of the area. The surface thermal trough exists between these two systems, typically produces hot, dry, and unstable conditions that can also result in dry lightning and strong gusty winds. And this pattern causes a lot of problems on the east slopes of the Cascades when the surface thermal trough crosses the Cascades and moves into the Columbia Basin. You can have tremendous wind, very low relative humidity, and a lot of times if there are any holdover lightning fires, they get up and take off, and extreme fire behavior can rapidly occur. Another critical fire weather pattern is the firn wind, east wind, and this occurs when surface high pressure pushes inland behind a cold front, becomes centered over eastern Washington, Idaho, and Montana. You have strong pressure gradients across the Cascades, producing strong winds, very low relative humidity, and hot temperatures. And once the winds cross the Cascades and move downslope, you have adiabatic warming there, and so air warms at 5.5 degrees per 1,000 feet, and you have a corresponding drop in relative humidity. This can result in rapidly developing extreme fire behavior when these east winds hit the area. This pattern is most common in September and early October. This is an example of an east wind case, September 21st, 2009. The right-hand or left-hand panel here shows a surface pressure pattern at 1200 UTC, shows the surface high over western Montana. Thermal trough has developed along the Washington and Oregon coast, and very strong pressure gradient across the Cascades. Meanwhile, at the upper levels, this pattern is a little bit different in that this is not a breakdown of the upper level high pressure critical fire weather pattern, but rather a building of the high pressure area pattern. High pressure in this case is building off the coast, and it produces strong winds all up and down the Pacific coast when this occurs. In this particular case, we had wind gusts in excess of 35 miles per hour. The relative humidity in southwestern Oregon dropped down to less than 10%. Also, is little or no humidity recovery overnight. And on that day, 2 new large fires broke out in southwest Oregon. The next region we're going to look at is California. Fire season extends from mid-May through October in Northern California and from late March through December in Southern California. However, during drought years, the season can expand the entire year in Southern California. And again, primarily firn winds, north and mono winds, most common in northern central California. This occurs when strong high pressure builds into the Pacific Northwest and strong pressure, north-south pressure gradients over northern California for the north winds. And mono winds occur when the high pressure gets centered more into Nevada and produces strong gradient across the Sierras, and also your downslope warming and drying. Southern California, you have Santa Ana and sundowner winds. Same process again. High pressure builds into Nevada, Utah, northern Arizona, resulting in strong pressure gradients across Southern California. And one thing that fire weather forecasters look at is pressure gradients between western Nevada and the LA Basin. It seems to be a good predictor of Santa Ana winds in Southern California. I won't go into too much Santa Ana and sundowner winds because the first webinar in the series dealt a lot, provided a lot of information about firn winds in California. And the last critical fire weather pattern for California occurs when a large closed high pressure center develops over the Great Basin and extends far enough west to produce a heat wave over California. And when small upper level troughs slide up the west side of this high pressure center, can produce dry lightning and tremendous outbreaks of ignitions. This is an example of Santa Ana wind event in October 2007. This is the surface pressure pattern on the left here, showing the center of the high over the Great Basin. Well-developed surface pressure gradients over Southern California. And again, you see in the upper level pattern on the right-hand side here, the upper ridge is off the coast and building into the area. Winds in this case exceeded 50 miles an hour. RH was less than 10%. Numerous fires burned hundreds of thousands of acres, destroyed thousands of homes. Over 1 million people were evacuated, and unfortunately 10 fatalities in that situation. Here's a satellite picture showing the smoke columns. Here's San Diego was a big area, and then also up in north of the LA basin. But you can certainly see the direction of the wind as the smoke is being pushed off the coast there. Alaska region fire season extends from May through August, but is most active in June and July. And again, they have a pattern breakdown of the upper level ridge. Upper level ridge tends to develop over the interior portions of Alaska, and when a upper trough starts to move in from the Gulf of Alaska, that gets pushed north and east, producing moist, unstable air, and can bring dry lightning and gusty winds to the interior here. Example fire for that would be the June 1998 Carla fire, which experienced wind gusts of 35 miles an hour on RH less than 25%. Okay, so much for the looking at the regional critical fire weather patterns and a few fire case studies. Let's look at some of the tools that are available to fire managers and firefighters alike. And I'm going to discuss the geographic area predictive services products. There's a whole list of them here. The National Wildland Significant Fire Potential Outlook is issued first business day of the month, and it covers a 3-month period. I have an example on the right-hand side here for April and May of this year, showing that there is a significant wildland fire potential up in the Great Lakes this spring. During the fire season, there is a daily product called the 7-Day Significant Fire Potential. There are also fuel and fire behavior advisories that can be used to identify what areas are most critical from a fuel aspect. There are weather and intelligence briefings, situation reports, and resource summaries. Tools that National Weather Service produce, red flag warnings and watches, and have an example on the left-hand side here from July 22nd of last year, 2014. The areas in pink, I guess those should be more red, but at least in this color combo they're pink. There are the red flag warnings, and the yellow are the fire weather watches. And the red flag warnings mean that extreme fire behavior or fire weather conditions are occurring or imminent based on weather patterns. Folks in the field can also request spot weather forecasts for their incident to get an idea of what may be coming their way as far as a critical fire weather pattern. The Storm Prediction Center produces the fire weather outlooks on a daily basis, and I think they go out to 3 days. And they have a nice graphic outlining the areas that they see from a weather pattern situation that could cause fire problems. The Weather Service also has web-based fire weather briefings and farsight data streams for the AF bands. So looking at the summary here, tracking the development of critical fire weather patterns is essential in identifying days when large wildland fires exhibiting extreme fire behavior are most likely to occur. And from the literature research, see some knowledge gaps here where more research would be beneficial. One is determine a study to determine the frequency at which these critical fire weather patterns occur. Don't have any good handle on that right now. We'll also need to get a better understanding of the dynamics of critical fire weather patterns, which ones are stronger, which ones have higher probability of producing extreme fire behavior. And lastly here, we don't have a mechanism now to input atmospheric stability into any of the fire behavior prediction models. Right now we're basically using what information we have subjectively to kind of evaluate how atmospheric stability may impact fire behavior during the day. I added here a couple of additional links to publications or websites that can give you more information on critical fire weather patterns. And this first one here is a National Weather Service 1993 Critical Fire Weather Patterns for the United States. It's Fire Weather Training Report, and it's available online from the Northwest Coordination Center at this link. Also available from the Desert Research Institute Program for Climate, Ecosystem, and Fire Applications, Critical Fire Weather Project. This is a very nice product here where critical fire weather patterns are defined and new fire case examples presented for the different geographic areas in the United States. So with that, pretty much concludes my webinar here. I take questions now.
All right. Thanks, Paul. That was a very interesting presentation. You covered a lot of ground there and did it very clearly and well organized. That was very, very much appreciated. There's a few questions have already come in, so I'll start into those already. The first one is from Porfirio Chavaria, and they ask, what is the average duration of these upper-level ridge events? How quickly or how slowly do these events pass? What's the frequency during a typical fire season?
Okay, there's a lot of questions in there, and again, there's very limited research into that. I can give you a little bit about my own independent research in the Pacific Northwest, Washington and Oregon, and the frequency in which breakdown of the upper level ridge occurs could be every 8 days during the peak of the fire season. Now those are not all extreme fire behavior conditions, but anyway, there is the frequency there about every 8 days upper level trough and breakdown of the ridge occurring. And typically that spans 2 or 3 days at most. Like I said, there's very limited research, and I would expect that these values that I see in Washington and Oregon could be vastly different in other parts of the country. But I think the bottom line is that they occur more often than people realize, but what is oftentimes the driving factor in whether they present problems or not is the condition of the fuels, how dry they are, how susceptible they are to ignition and rapid fire spread. Drought also becomes an issue there. So that's about the best I can answer for right now until we have more research.
Okay. The next question is from Robert Kowalski, and he asks, the West Texas dry line case, is this similar to the Southern Plains outbreaks that were common a few years ago?
I haven't looked at those in particular, the Southern Plains, but I would surmise that they're probably very similar. To get a large fire outbreak like that, you need dry air, and you need a mechanism that moist air, high dew point values are shoved east of the area, and you get the downslope off the Rockies, very low dew points and low relative humidities, and also the strong winds. So my best estimate is probably that they were caused by the same mechanism.
Okay. Next question is from Mike Conley. I think I know Mike. How you doing, Mike? You've mentioned the ridge breakdown and the Chinook jet stream alignment a few times. Do both of these elements need to be present for the extreme fire weather we've been discussing? Will we have similar extreme behavior if each is present independent of the other?
Okay. The Chinook winds, the way I see it, is the result of a breakdown of the upper level ridge. And to get the intensity of the jet stream that is perpendicular to the Rocky Mountains there, you just about need the ridge to break down to the south, allowing the jet stream to move in over the area. So with the example of Chinook winds, I would say those are probably the result of the breakdown of the upper level ridge, whereas the firn winds along the west coast are not. They are a result of high pressure building in aloft from the Pacific Ocean. So they're at the leading edge, eastern edge of the high pressure area, whereas the Chinook winds are at the west or northern edge of that breakdown.
Okay.
So hope I answered his question there.
Okay. Next question is from Julie Titus. She says, in Northern California, the Southern Cascades, Klamath Mountains, specifically in South and Central Siskiyou County, we had an unusual wind pattern that dominated much of this past summer. They were south winds similar to what we usually experience in prefrontal passages in winter. Example, the Bulls Fire in Wheat, California. Can you explain if there was a prevalent and uncommon synopsis correlated with this?
I wonder if she could clarify what time or what month that was in.
Okay, let's see, Julie, could you type that in real quick? September.
September. South winds in Northern California are usually a result of strong troughs moving into British Columbia and Washington and northern Oregon. So that would be my best estimate of why those southerly winds developed. But without looking at the exact days and the exact pressure patterns, that's just a guesstimate on my part.
Okay. Jessica Block has a question. Where can I get rudimentary training on how to interpret weather maps? I'm a geologist and reading these contours is not intuitive to me.
Oh, okay. I think that there are a number of sites, National Weather Service sites, that I don't have any in particular, but I know that the Weather Service has sites that explain the different charts, and I would just suggest that he get together with his local National Weather Service site or do a Google search. Another alternative, there are a number of universities that offer meteorology degrees, atmospheric sciences. Think University of Washington, San Jose State, University of Utah. For the western states would be good places to look for. So I know they're online. Look at National Weather Service sites and some of these university sites.
Okay. Brian Potter has a note. He says, Hull et al. 1966 describes frequencies of the critical patterns from Schroeder et al., but only briefly. Unfortunately, I doubt the data it describes still exists at the Pacific Southwest Station.
Okay.
Next question is from Clay. Oh, I'm going to screw this one up, Trey. I apologize in advance. Trauernicht? Clay Trauernicht. Are there indicator variables that can be derived from weather records / models that can be used to characterize atmospheric instability in order to attribute this to prior fire incidents?
I would say if he's looking for archive situation, the University of Wyoming has a good archive for upper air data. That would be one site if he had a particular incident and day in mind. Another possibility would be to look at Wildland Fire Assessment System has an archive for Haynes Index days. So that would be two locations that I could direct them to.
Okay. Eric Croner asked if this webinar is going to be available on the Lessons Learned site for viewing in the future, and I can take that one. Yes, we record all the webinars. I upload them to the Advances in Fire Practice page. It's within the Lessons Learned Center site, and they're archived on the Lessons Learned Center's YouTube channel. If you come to Advances in Fire Practice in an hour or so, it should be up there. Next question is from Jose Luis Duce Arguez. He says, very interesting, thank you. Now, as a firefighter fire manager, how do you think all of this great critical information can be transferred to the practical firefighting world? I mean, we are conscious of these critical fire behaviors, but which is the best way we have to transfer that to the ground level?
Okay, that's a good question, and one of the reasons why Joint Fire Sciences funded our group of authors to produce this synthesis of knowledge of extreme fire behavior. Volume 1 was for fire managers. Volume 2 is going to be for a little more technical people, FBANs, meteorologists. So that is one mechanism. One of the things we hope that will be result is that this material will become available in the training sequence, and I know that critical fire weather patterns was taught in the S590 course to FBANs for many years, and in the new version it has been also included in the S490 level. Things that a regular firefighter can do in the field. And one thing I wanted to emphasize here is that relative humidity is really a critical element in every large fire and extreme fire behavior case that I've looked at. And when you go into a new area, if you're on a crew or something, I think it is really imperative that you get with the locals and find out what these critical relative humidity thresholds are. And that's something you can monitor with a belt weather kit, a little Kestrel. You can monitor the relative humidity changes during the day, and if that relative humidity drops below that critical threshold, you can very well expect to see increase in fire behavior. And when I was an incident meteorologist working on fire teams and large fires, that's one of the techniques I used, is to identify the critical relative humidity of that area and key on that on my briefings and fire weather forecast. And it usually worked out quite well to timing the time when fire activity really increased during the day. So those would be my suggestions.
Okay. Gene Rogers has a note. He says the Fire Weather Ag Handbook 360 by Schroeder and Buck 1970 is still a great book for learning about fire weather.
That is a great book, and there is a fire climate chapter in there. Most of it is very similar to what was in the 1964 Schroeder publication on that I alluded to or in this presentation here. So the Black Fire Weather book, as commonly called, is also another good chapter to look at in there.
Okay. Let's see. Clay Trowernick just asked if you could repeat that reference, please. Maybe say it a little slower. I'm not sure which one. If you were, there was one that I said earlier was the Fire Weather Ag Handbook 360 by Schroeder and Buck 1970. And I think
yes, that is the citation for it. I think most forestry offices probably have a copy of that somewhere.
Okay. The next question is from Clara Quesada, and she asks, do you think that warning fire weather risks? I'm sorry, Clara, I'm going to have to interpret this a little bit. Do you think that fire weather risk tools are clear enough to people in order not to use fire? I'm not quite sure what you're asking there, but maybe sort of what Paul's been talking about with sort of critical fire conditions for looking at prescribed burn windows, maybe? I'm not sure. I'm not sure what you're getting at there, Claire, but can you see that one, Paul?
My only comment to her would be to get with your local National Weather Service office, discuss your project with them, set up a systematic way of getting spot weather forecasts, and work with your burn prescriptions on that. Yesterday's webinar talked a little bit about the Mac Lake fire in upper Michigan, or the northern part of lower Michigan, and they set out to do a prescribed burn right in the face of a critical fire weather pattern. Dry cold front went through and just was a terrible mess. Resulted in one fatality. So when you do prescribed burns, you've got to watch out for these critical fire weather patterns too. And again, work with your National Weather Service office in that.
Okay. Well, Paul, that's all the questions we have now. Thank you for a very interesting and very well done presentation.
Well, thank you very much. I hope people were able to get something out of it.
And thank you to the audience as well. We have more webinars on extreme fire behavior coming up in the next few months. So check the Advances in Fire Practice website for that if you're not on our mailing list, for getting the announcements for the webinars. And hope we'll talk to you. We'll see you the next time. Thanks.